chapter 12. And this could be a much longer chapter where you do analytic geometry that this whole section is about. And it's all about conics or conic sections. We'll just call it conics for short. And what are conics? Well, if you take two hollow cones and you invert one and another, and they're hollow, and then you start passing a plane through it at different orientations, you get cutouts of different geometric objects. I'll just show you in the textbooks what some of them look like. You can see it as well in the textbook. So here's the two cones, and then if you put a line straight through as the first thing here, the cutout that you get is a circle. Tilt it at an angle, you get something called an ellipse. Keep going and tilt it at another angle, you get something. If you look at this, these cones go off to infinity, I should state. But then you get something called the parabola, and over here you get what cutout tends to be a hyperbola. And that's what you kind of see there. If you start cutting them out, that is what you physically get. Okay, so these are conic sections that we're going to be looking at. So we're going to start this first section by looking at a circle. But before we go to that, let's talk about how we're going to define these. We're going to define these by something called a locus. A locus is a set of points that are defined by an algebraic or geometric condition. So a set of points defined by an algebraic or geometric condition is called a locus. Or sometimes they call it a locus of points. So that's what we find, word locus. So we're going to be defining a locus, a set of points for a variety of those different objects that we just kind of showed you pictorially there. The first one is going to be a circle. And the definition we give for a circle is very simple. A circle is a locus of all the points in a plane, of all the points in a plane that are a fixed distance from a given point. Plane that are a fixed distance from a given point. So meaning if I have some point in the plane and I get my fixed distance over here, like you tie a string to it, you might have some sort of a string out here, and then you rotate around that plane. That will give me, I'm not going to draw it perfectly here, but it gives you the idea of a circle. That's what it is, a fixed distance d from a given point here, or r, let's call that r. That fixed distance will be r. Okay, from that definition, can we get a geometric definition? It's a word definition talking about geometry. Can we get an algebraic representation of a circle? And the way we're going to do that is we're going to throw it into, if you will, an XY coordinate system. So that's what we'll do. We'll try and algebraize it now and pick some generic point over here, h comma k. That's the center of the circle. There's the center. And then I go out a fixed distance, and we call that distance r. And then as I sweep it around, I get this idea of a circle. Okay, so this is a point that's on that circle, and it has some generic coordinates, x comma y. So that's a distance. Let's use our distance formula. And let's do it over here. Here, we'll use the distance formula. So we have 2 points over there. We have one point coordinates x comma y, the other h comma k. So my distance formula, the distance, which is I'm calling r, I'm giving the name r for the radius, is just my x minus my x coordinate of that one point, h quantity squared, plus y minus k squared square rooted. That's just using the distance formula, another geometric analytic tool that we have. Then what do we do here? Square both sides, and I'll flip it around, and you're going to get x minus h squared plus y minus k squared is r squared. So from this word definition, we were able to, about the geometric conditions that need to be satisfied, we're able to get an algebraic representation of that circle of radius r that's centered at the coordinate h comma k. Okay, so how do we use this? What sort of problems might you see? Very simple. We're just going to be applying this formula. Now, this is called, we give this a name, and this is called the standard form. Now let's just write it out here. This is the standard form. Of a circle. And its radius are centered at h comma k. X minus h, y minus k, quantity squared is r squared. We also have a general form. When you multiply everything out, there's another form of the circle. There's the standard form, and then you also have a general form, which might look like some, I'll put it with an x squared plus y squared. I'll put x squared plus y squared plus a times x plus b times y is equal to some, or plus c is equal to 0, where a, b, and c are just real number constants. C, in this case, will have to be a negative quantity. Otherwise, you can't have a circle with a negative radius. It's impossible. So we have a standard form and a general form. So how do we use this and what do we do? So, for example, here's some problems. One is find a circle of radius 4, and by circle we mean the equation for a circle, centered at -3, 2. Okay, this is a simple application of using the standard form. So I plug that in, my h is -3, so it's x subtracting -3 quantity squared plus y subtracting 2 squared is equal to 4 squared. So it's x plus 3 squared plus y minus 2 squared is equal to 16. And we could leave it in that standard form. That's a very simple application. Now where it gets a little more complicated is when you're given this form and then you're asked to find the radius and center of the circles. That's where it gets a little more complicated. So let's take a look at an example of going from here to there. So that's our second example, second type of example that you will see when you're asked to find the equation of a circle, or now find the important features of that circle, its center point and its radius. So find the center and radius of a circle given in the general form, and here's x squared plus y squared, let's see, minus 2x, so minus 2x plus 6y, and minus 2 is equal to 0. So what I want to do with this is kind of get into that standard form, like that, something of that form. So I'm going to have to complete the square for both the x and the y. So let's just separate these out. I'll put the x's together. So x squared minus 2x, put a little space between them over here, plus y squared plus 6y. And let's move that 2 over to the other side of the equation. So I just put some space over here. Now I'm going to complete the square on this. So what do I do to complete the square? So that's what we're going to be doing. We're going to complete the square. Well, we've done that before, so why don't you try that? Complete the square on both of these and see what happens. I'm going to do it as well, but I want to make sure you kind of work on that. I'll write it out after I complete the square over here. Okay, then we'll see how I got that by completing the square. Any questions on that? Is that okay? So we're all okay with that. Okay, good. It's like people are kind of learning how to do these things, hopefully. Okay, now we can answer the question over here. You know, find the center and radius. What is the center? So the center is simply, it's always the negative of what's in there, because remember it's defined as, you know, x minus that value. So the x coordinate is a positive 1, and the y coordinate is a negative 3. Now the radius is the square root of what's on the right-hand side, which I can simplify to 2 square roots of 3. So I can pull out 4 out of the 12, the square root of 4 is 2, and it leaves behind the 2. So I have a circle whose center at 1 comma negative 3 with a radius of 2 square roots of 3. So it's very simple. So we've done that before, so it doesn't seem to be too complicated. So we're okay with that. That's about everything we need to know about a circle, given it either standard form, general form, and completing the square. Now, sometimes you can't do it. For example, if you had something else like this, if this was, say a 13 over here, a plus 13, you would do that and you would not get a circle. So this doesn't always define a circle. The numbers have to work out, because if this ended up being a negative quantity over here, it wouldn't work out. I wouldn't be able to have a circle. It doesn't kind of satisfy that. Okay, so let's take a look at the next conic section. That was the circle, which is 12.1. Today we're going to look at 2 conic sections. And the next class is the ones that are parabolas. This gets a little more complicated now. The circle is the easiest one by far. So the next thing is a parabola. So 12.2, all about parabolas. And let's put the definition. So a parabola is the locus of all the points in the plane equidistant from a fixed point. So equidistant from a fixed point and a fixed line. Now the fixed point is called the focus. It's called the focus. And the fixed line is called the directrix. So the fixed line is called the directrix. So if I want to get a picture of what that is, I have some fixed point, call it F for focus. And then I take my fixed line over here, there's my directrix. And I want to be all the points that are equidistant from that. So I go halfway between my focus and my directrix, and I can get a point that's halfway between. So that distance is the same. So that distance and that distance are the same. Now if I move away, say I move to another point, this point over here, this distance is the same as that distance. It's a direct, straight down distance to the line. Move away even further, I get this distance and that distance are the same. And you'll trace out something that looks like that. And if that's D, that's D, that's D1, that's D1, that's distance 2, distance 2. The distance stays constant. So that's what we have. Okay. How can we come up with a algebraic form of that? Well, we're going to make this a little bit easy. We're going to put our, if you will, our coordinate system. So it's right, this little point here, we're going to, as we know, that's a parabola, so that's the vertex. We're going to put the coordinate system at the vertex. So this is what I'm going to set up over here. So the goal is to get, from this definition, an algebraic representation. So here's my point, call that my point, if I want to call a point, the focus, and I'll give it coordinates. So I'm going to call that the focus. And I'm going to give it coordinates, 0, comma, p. So this distance here is p. So the distance from here to here is p. And then I take a line that goes just underneath that. That's my directrix. And that's also a distance p down this way. And this is y is equal to the negative of p, positive p, negative p. And again, we want to sweep out the graph of those lines at this distance and that distance maintain the same value. It should look something like this. You can see if you had that and just keep maintaining the same distance. So let's take a generic point on this graph. Okay, so I'm going to pick some generic point over here on the graph. That's my point x, comma, y. And what do I want to have happen? I want this distance here, that distance, and this distance. They don't show to be equal. This parabola would have to be a little wider, but that's okay. And this distance here. So the distance between those 2 points and this line straight down, I want that to be the same. So you can see, since this is a little bit shorter than that, my parabola should be a little bit flatter than I've drawn it there. That's okay. We get the idea. Okay, so now we're back to our distance form, just like we did for the circle. So let's look at that. So let's go and take a look at getting the distance between those points that are specified. Now we should point out that this point here has coordinates too. Notice I'm going straight down. So the coordinate of this point is just x. Y is always the same, negative p. So I have these 3 points that I'm working with, 0 comma p, x comma y, and x comma negative p. So let's find the distance over here, and just for now, I'll call it d1 and d2, and the condition is d1 has to equal d2. So what is the distance? Call that d1. Well, that's nothing more than if I take my x minus my x coordinate, so it's x minus 0 squared plus y subtracting p squared. So that's that distance right there. Or I can simply write that as the square root of x squared plus y minus p quantity squared. Okay, let's take a look at that distance d2. So what do I get? I get x minus x, so x minus x squared plus y minus a minus gives me a y plus. So it's minus a negative p quantity squared. That goes out, so it just gives me the square root of y plus p quantity squared. Now I could take it and just write it as y plus p, but what I'm going to do is I'm going to set both of these equal to each other. Now I could simplify this, but it doesn't pay because the next step will be easier to deal with. So if I turn around and set d1 equal to d2, then I'm looking at my x squared plus y minus p quantity squared square rooted is equal to the square root of y plus p quantity squared. And then I'm going to square both sides. So I'll now square both sides. That will give me the new algebraic expression. But if the distance is equal, then the square of the distances have to be equal as well. Just going to allow me to get rid of those radicals so I can actually manipulate it better algebraically. So what do I have? I now have on the left-hand side x squared plus y minus p squared is equal to y plus p quantity squared. Need a little more of the black cartridge over here to get this to work. We're running out of ink. So I'm going to square both of those binomials out after I reload and get some fresh ink in here. And we'll try and simplify that and get an algebraic representation for that. Okay. So let's turn around and square that. So I get x squared plus y squared minus 2p plus p squared is equal to y squared plus 2py, excuse me, 2py, and then we end up with a plus p squared. So x squared minus 2py plus p squared. Then you can see what happens over here. Y squared, p squared, p squared. And then I can add 2py to both sides, and this simplifies to x squared is equal to 2py plus 2py gives me 4py. Now that's my, y is equal to x squared. Now, we can show this. It's a little more complicated. I'm not going to do it, but this is the, if you will, the parabola that opens upwards centered at the origin or whose vertex is the origin. This is an equation or a parabola whose vertex is at the origin and opens upwards. So again, we draw that picture. Here's my, and that's it. Here's my p-value, and here's my directrix. And it opens upwards. If we were looking for one that opens downward, well, then we would shift over here, and this would turn the other. So if I wanted to get one, the algebraic form for a parabola that opens downward, then my p would be here, and my line, my direction, p would be at negative p, and I'd be looking at something that opens downward over here. The change would put a negative over here. That's the only thing that would happen. Then it would give me x squared is negative 4py. Now you can show that simply by redoing what we did. This would be a positive p, that would be a negative p. Square everything out, this would be a negative, that would be a positive, and just move it over and get negative 4py. Same thing would happen. Okay, now what if I wanted it a little more generically, and instead of having the vertex here, move the vertex to another generic point, call it h comma k. So there's another form of that I can do, because there's many different forms. We're just doing this way. We're going to show you some others as well. So the other form is now we want to put the vertex at the point, say, h comma k. We could do that as well. It's a more complicated thing to set up over here, but when we do that, I'm just going to show you the end result. You'd end up, for the one case, you'd have x minus h quantity squared is equal to 4py minus k. That's vertex centered at the origin, that opens upward. We could then turn around and vertex at h comma k that opens upward, vertex at h comma k that opens downward. Okay. Now we could also have the parabola open up either to the left or to the right. So there are other variations on this theme we could do too. So we could have a parabola that opens in a different orientation. And you could go through the same analysis we did here, and we could have it either opening this way to the right. And in that case, when you look at that option, and if I center it at some point other than the origin, it will look like this. So now you have y minus k squared is equal to 4p x minus k. Now if I wanted to open up to the opposite direction, I get the fourth form of that. Y minus k quantity squared is minus 4p x minus h, h. So those are four types of parabolas. They either open up straight up and down or left to right. Now, there are other types of parabolas that we could do. They're much more complicated. We could get a skewed one, then we could open up a parabola and have some other fixed line in this direction and have it over here, and it could open up, say, in this direction here. We're not going to do those. So we're not going to, they're either going to open upwards or downward or left to right, and then just shift it in the plane. But you can see where you can get a lot of different things for a parabola, unlike the circle, which was so much easier. So those are roughly the four forms written in their standard form. So that's the standard form for all of those parabolic equations. So these are the four standard forms. Okay. Now, what is typical that you are asked for? Well, you're asked to do one of two things. First thing, you might be asked to find the standard form of equation given conditions such as where it's centered and the distance or the location of its focus. So let's take a look at, this gets a little more complicated. Let's say, for example, let's say we're given the following. Let's take a look at this way. Say you're given, here's an example. Y is equal to x squared. And what you would like to find, they might say, analyze the parabola. And what does that mean? That means find P and the directrix. Analyze the parabola. So you want to find its, where its vertex is. And you analyze the parabola, the vertex. You also want to find out where its focus is. And then you would also like to find its directrix. As an aside, while I'm here, let's take a look at why they even call it a focus. Why do they call it a focus? Do you understand why it's called a focus? Well, if you take a parabolic mirror, let's say a parabolic mirror, and you shine light. That's typically if you're looking at the stars, and they make some telescopes that have parabolic mirrors on them. Well, the light will come in and reflect off, and no matter where it comes in, it'll reflect off and always go back to the focus. No matter where it goes, it'll always go to that focus point. It's focused there. Same thing is true as sound waves. That's why in certain, music halls, there are certain points in that music hall, if it has a parabolic shape, where you can hear the subtle instruments that are playing very loudly because it gets their sound coming from here, amplifies, and then just goes all to one location. In fact, there's a story of a woman who was an aristocratic woman. She would always go into a music hall and ask for the same exact seat. And before the people started playing the music and everything, before the musicians started playing, she would sit there and she could hear people gossiping, and she'd hear them very clearly. So she would sit there, could hear what they were saying because she was at the focal point, so she could hear all their hidden secrets. They thought they were just whispering to each other, but their whispers came down and kind of all focused at one location. It was more of an elliptical shaped room, but that's the idea. That's why it's called a focus. It's where things get focused. I just figure that's an aside on why even we call it a focus. Okay, so let's analyze this one. So we're looking over here, and you're comparing the two. So the closest comparison, I have an x squared, and it's positive. So this is the closest comparison. So if I'm looking at this, let's flip it to the other side. I get x squared, is equal to y. So that tells me right away, I could write it like this, x minus 0 squared is equal to 4p times y minus 0. So it tells me my vertex is at the origin, if I kind of try and fit it into that form. So the vertex is at the origin, 0, 0. Well, the focus is going to be that y coordinate. Remember, it's going to be 0. Once I know this, 0, p. I just add, it's, if it was the center, it would be h, k plus p. If it was centered at, the vertex was at another location, but it's not. So I have to find what p is. So this gives me an equation to solve for p. So it tells me then 4 times p is equal to 1, or p is equal to 1/4. So that's the focal point of that. So for this one, it would be 0, 1/4. Well, what about the directrix? Well, since it's vertex is here, the directrix is the line, y is the negative of p, that's how we define that. So in that case, we get y is equal to negative 1/4. So if I was analyzing that, I found its vertex, its focus, and its directrix. And let's kind of show it geometrically, and then we'll do another couple of examples. So if I want the picture of that, here's my XY coordinate system. Let's go out to, say, 1, 2, so its vertex is here. And I go 1/4 of the way up, and here's my focus. And 1/4 of the way down over here, and there's my directrix. So doing that and keeping those distances the same, my parabola would look something like that. And I'm trying to match the distances over here so that, say, for example, this distance here is equal to that distance there. Not quite, so I'd have to actually move it up a little closer this way to get it to work out. You can see if I want to make these the same, I should make this a little bit closer up here. It kind of tells you the shape of that parabola. Now, I can't do it by eye very easily, but the calculator and the computer software can do it. So there's my vertex, my focus, and my directrix. Okay, let's try another one now where we are no longer have my vertex, say, at the origin. Let's take a look for another vertex that's not at the origin. Well, in fact, I'm going to make it easy. Yeah. We could shift it off the origin, but for this section, I don't want to go into so much detail because we've covered so much in this course. So for the sake of hour, we could do that. It's easy enough to do. It's a little more algebra, but I'll make it easier on you guys. We'll always have the vertex at the origin. But now let's flip it around in another way. Let's say, for example, we have the parabola that looks something like this. Here's another example. So again, I want to find the vertex, the focus, as well as the directrix. So let's say I have y squared is equal to a negative 1/8 x. So over here, this is going to be a parabola that's opening up on its sideways. Okay, we have a different idea over here. So that's the form we're comparing it to is y squared is equal to a negative 4px. That's the general form. That is a parabola that will open up in that direction. Okay, see if you can find those features. Vertex, find the focus, and as well as find the directrix. Switch it up. See if you can generalize what I just did and find those three features. The focus is easy. The vertex is easy for all of them. It's all the same. The focal point as well as the directrix are a little bit hard. They switch over. See if you can understand what's happening. And I'll do it. Let's see if you can figure it out on your own. Best if you can do that, because then you're actually learning it better than just having me show it to you. You kind of reason through it and you understand it better when you do that. put it over here. Vertex is easy. Doing it in my head, so I might switch things around, so I'll see if everything works out okay. That should go the other way. I don't like that. Kind of opening up the other way. That's why I'm not liking this. It should open up the other way. Let me just see. Draw this picture over here in my head over here. So if I put my focus here, having it open that way, it should open the opposite way. So it should be, we're going to compare, when it's this way, we have to compare it to minus 4p. So y squared is equal to a negative 4px. That's what we have to do. That's what it is. Yeah. So we got to be careful. We're not comparing, when it's negative, we have to compare it to its standard form with the negative out in front. That way it will open up in the correct fashion. Yeah, that's right. Okay. When it's negative, I have to compare it to the standard equation for the negative value. That will open it to the left. Now, does anyone want to see how I got those values for the focus and the directrix? Anyone want to see how I found it? Okay, let's compare it. So when I have a negative, I have to compare it to the similar form. So this is of the form y squared is negative 4px. Okay, so I can see the vertex is simple. If I don't have any of the, y's or any other constants sitting there, then I know that it is always passing through, the vertex is always passing through the origin. Because it's negative, I know that it's a parabola that goes this way. So over here, I make the connection that 4p, that's my primary thing, is finding p. So it tells me 4 times p is equal to 1 over 8. I want to solve that for p, so I divide both sides by 4. And that gives me p then is equal to 1 over 8 times 4 is 1/32. Okay, now this, the other one, went with my vertex was along the focus was along the y-axis. Over here, this p has to be along my, so now the p is over here, but this is the negative of p, so what do I have to put over here? When I get the p here, I turn around and it's always equal to the negative of p comma 0 for y, because that's the coordinate right here. This is my focus right here, which is negative 1/30, and my y coordinate is 0. Now this is a line of constant x value, and x is equal to a positive p, 1/32. So, you can either do it that way or look at it this way and then say p has to be negative. Yes, The other way is to just do it this way. Yeah. P would have to be negative, and then it's negative, negative. Then I could do this negative, and then take the negative of the negative for my vertex, which is on the opposite side. So the vertex is always x is equal to the negative of P over here. You could do it that way. Yeah, let's just compare it to this one. You could do it two different ways. Make it easy on yourself. So in this case, we see that P turns out to be negative, so that means it's my focus point over here. This is the focus to that side. There's the directrix. So I want this distance and that distance to be the same. So what happens over here, it opens up that way. Okay, let me give you one more to try, and then, well, in fact, we're pretty much done. So let's just end there.